Let's find the Maclaurin series for tan inverse of 3x. This one will require using some ideas that we haven't seen before. So here's what we're going to do. We're going to remember the tan inverse of x. If I take its derivative, is 1 over 1 plus x squared. So what we're going to do is we're going to use the Taylor series for this and then take its integral. Because tan inverse of x, will be the integral of 1 over 1 plus x squared dx. That's the idea. If we turn this into a Taylor series, it's an infinitely long polynomial. Finding antiderivatives is just one term at a time. So this will be integral of 1 over 1 minus negative x squared, so that we can turn this into something like 1 over 1 minus x. But if it's 1 over 1 minus something, then that is the something to the n. X to the n, from 0 to infinity. And we're thinking about this as an integral of an infinitely long sum. So that's integral of the sum from 0 to infinity. If I distribute that n, that makes negative 1 to the n, x to the 2n, dx. And now we're thinking about applying the integral to each term in the sum. So essentially we're distributing that integral sign inside the sum. There are some technical details about what's going on here. You can't do that for every single function, but you can do it for most, well, for many, but it will work for everything that we need to do. Essentially what we're doing is we're interchanging the sum in this integral, so it will be the sum of the integral minus 1 to the n, x to the 2n, dx, and then we just integrate this into n for the integral. If we think about this integral right here, each term in the sum is a constant term and is fixed, which becomes, since n is a constant, it will not change in the integral. So that will be still minus 1 to the n. An integral of x to a power is 1 more in the power, and then divide by the new exponent. Okay, so we do have to be a little bit careful with one last piece. The issue here is that when we integrate, we have a plus c that's in the end. So we actually do have a plus c. This would have been from 0 to infinity. This is from 0 to infinity. But now when we plug 0 in, this will become x to the 1, x to the 2 times 0 plus 1. So after we've integrated, the first term is actually the x term. The constant term that's at the beginning will be this plus c that we get from our constant of integration. So we do need to figure out what that constant of integration will be. Let me just save what we've actually come up with. We've come up with that this Taylor series for tan inverse is everything we've got there at the very end. So we've got tan inverse of x becomes sum 0 to infinity minus 1 to the n, x to the 2n plus 1 over 2n plus 1, and then plus c. Let me just write out some of those terms. If I plug 0 in, negative 1 to the 0 makes it positive. X to the 1, that's x to the 1, and that's 2 to the 1. So that will be x over 2. I'm going to put the c at the beginning. When I plug 1 in, I get negative 1 to the 1, which is minus. And so now these are going to be odd numbers. So that will be x cubed. This exponent is, if I plug 1 in, 2 to the 1, which will be 2 squared. Oh, sorry. I don't mean to, I missed my exponents. This should have been 2n plus 1, right? It was the new exponent divided by the new exponent. So this is actually exactly the same as this, so that will be a 3 and this will be a 1. Right? X to the 1 over 1. X to the 3 over 3. Now this will change signs. X to the 5 over 5. That makes it alternating. So minus x to the 7 over 7, and so on and so on and so on. So that's what we get for our Taylor series for tan inverse of x. But how do I figure out what c is? If I plug 0 in, so if I set these things equal, and then I plug 0 in, well then I better get c plus 0 plus 0 plus 0 forever on out. But tan inverse of 0 is 0. And so that reads 0 equals c, so that c is 0. So what we can say is that our Taylor series for tan inverse of x is this whole stuff without the c, because c is just 0. So I don't even need to rewrite it. Really what we've discovered is that this is our Taylor series for tan inverse of x. So how do I get the Taylor series for tan inverse of 3x? Well, I replace x by 3x. So I just plug a 3x in, and I get 0 to infinity, minus 1 to the n, 3x to the 2n plus 1 over 2n plus 1. And that's good enough, but we could distribute 0 to infinity minus 1 to the n, 3 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1. I like to have the x's separated out because we think about those as the variable in a polynomial and everything else is the coefficient. And that's it. That's the answer.